Hello, I'm Patty Simpson with Simpson Math. In this video, we're going to look at the equations of functions and find the domain from those equations. In previous videos, we looked at 7 parent functions and we learned to graph those 7 parent functions and learned to transform them. Did some transformations with them. We're going to continue to look at those same 7 functions for this video. And we're going to find the domain of those 7 functions. So let's start first with our linear function. And if you remember our linear function, the equation for our linear function, the parent was y equals x. And so some of the family members of our linear functions might look something like this, where we have y equals 3x plus 1. That's a linear function. Or 6x minus 2y equals 3. That's another example of a linear function. So remember that the way we know it's a linear function is our x, the degree of that function is just 1. The exponent on our x is just 1. Our x and our y's are not touching. The x is not in any sort of house, and so we know that that's a linear function. And all our linear functions, we've graphed them now. We've translated them or dilated them or reflected them, and we saw that all of our linear functions looked like this, regardless of what we did to them. They looked like that. Well, if we look at our input or our x values for the function, notice that there's no break in our graph. We can put any input in and we get out a real output. So we say that the domain of these functions is all real numbers. We can put in any value that we want for x. So in set builder notation, we say that x, such that x is an element of the real numbers. X can be we can put in anything into the linear functions, and we're going to get out a real output, a real y value. So for all of our linear functions, our domain will always be all real numbers. Then we looked at the quadratic function. For our quadratic function, the parent looked like this. Their family members might have looked something like this, where we had 3x squared plus 2x minus 4. There's an example of the family member. Or maybe it's in fancy function notation, where we have f of x equals negative x plus 2x squared, where the largest exponent on an x is 2, or the degree of this function is 2. That's what makes this a quadratic function. And again, we graphed the parent, and we might have translated it, did some translations with it where we shifted it around, or maybe we stretched it, reflected it. So all our quadratics had that smiley face or that frowny face shape to them. So the domain of those are our x values for all of those. Notice again, there's no break in there. So our x values can be anything. Wherever I look on my x axis, there is an output for every input. And also we saw that with our x values, we could put in any x value and we got out a real y value. So again, my domain is all real numbers. And in set builder notation, we write all real numbers, x such that x is an element of the real numbers, or in interval notation, anywhere from negative infinity to positive infinity. The next one we looked at was the cubic function, where y equals x cubed. And our cubic functions, the family members, looked something like this, where we have y equals 3x cubed minus 2x squared plus x minus 4, or maybe in that fancy function notation, negative 4 plus 1/2 x plus 6x cubed, where the largest degree on my x is a 3, or the degree of this function is 3. That's what makes this a cubic function. And our cubic functions reminded us of 3rd Street here in Temple, where they curved around like this. Some of the family members might be a little more dramatic, where their turns are a little more dramatic. Or maybe if we reflect it, it looks something like this. So those are all examples of cubic functions. And we also saw when we graphed those that we could put in any real number in for x, and we would get out a real number for y. So or you can see here, there's no break in any of those graphs. So for every input, there is an output. So again, my domain for all of my cubic functions will always be all real numbers. Then we looked at the cubed root function. Our cubed root function, the parent of it was the cubed root of x. And again, our family members looked something like this, where they had a cubed root in the function. Or we showed that the degree of it could be to the 1/3 power. That 1/3 means the cubed root. And my cubic functions are like 3rd Street sideways. So they turn sideways. And we saw again that we could put in any real number in for x, and we got out a real number for y. So the domain of our cubed root function was also all real numbers, from negative infinity to positive infinity. And then we looked at the absolute value function. Absolute value function, and the parent of that was the absolute value of y, or a family member might be 1/2, that is going to dilate it. And then we've got a horizontal translation and a vertical translation going on. We did all that with our transformations. And the picture, or our graphs of all of our absolute values, looked something like this. Maybe they got dilated or reflected, but they all had that nice V shape to them. And again, we said that we could put any x value in for any real number in for x, and we got out a real number. So again, our x value is all real numbers for those absolute values. So notice that those 5 parent functions, 5 out of the 7, if I give you an equation for any of those 5 functions or their family members, then we know that the domain is all real numbers. I can put in any x value into any of these functions, and I'm going to get out a real value for my y. So we just need to remember that those 5, the domain is all real numbers. Now there are 2 of our functions that had restrictions on the domain. The first one was our square root function. Our square root function remember that our square root function looked like this. When we graphed it, it looked like that. Notice that there is a restriction on it. The graph doesn't go all the way across. There's no output or if I input here, there's no output, no real output. So we had a restriction on our square root functions. And so when we graph their family members, the way we determine the domain of our square roots is we know that the underneath the radical must be positive. We cannot put a negative underneath the radical. So underneath the radical must be positive. This underneath the radical must be positive. So what we are going to do is we're going to take whatever's underneath the radical, and algebraically, under the radical, we're going to say it must be positive. So if it must be positive, that means it has to be greater than or equal to 0. And then we're going to solve it. So to solve for the domain of all of our square root values, all of our square root functions, all our square root functions will have a restriction. And the restriction on the domain is going to be we're going to be able to find that restriction just by taking what's underneath the radical and setting it greater than or equal to 0 and solving for it. Then we also had another function that had a restriction on the domain, and that was our rational functions. If you remember when we graphed our rational functions had this asymptote so that they looked something like this. And as we translated or transformed our graphs, that asymptote just shifted around with us. But there was always this break in there. So the rational functions also have a restriction. So remember the rational functions when my x is on the bottom of in the denominator there. And the restriction there, what caused the asymptote was the fact that 0 cannot be in the denominator. So if I take some family member, like 1 over x plus 4, the bottom, the denominator, could not be equal to 0. So there's a restriction, can't be equal to 0. So what we're going to do to solve for that, or to find the domain of our rational functions, is we're just going to take our denominator and we're going to set it not equal to 0 because it cannot be equal to 0, and then we're going to solve to see what our domain is. So of our 7 functions that we learned to graph, the 5 of them, the domain is always all real numbers. But anytime we have a square root function or a rational function, there is a restriction on the domain. And we have to, the way we're going to find that restriction, if it's a square root, we're going to take what's underneath the radical and set it greater than or equal to 0 and solve. If it's a rational, we're going to take what's in the denominator and set it not equal to 0 and solve that. In the next video, I'll do some examples of finding the domain of various equations. Math made simple at Simpson Math. Thanks for watching.